Okay, so let's go into edit distance, one of my favorite dynamic programming problems. So the basic problem is to define similarity between strings or words. And a classical application, of course, is spell checking, right? You have the list of words in English or list of words commonly used. English is one of the languages that is huge. So English has, because it's so old, so English, I think, has like 400,000 words, but of course, in common use, it's maybe 40,000 or 50,000. So it's definitely a short list, relatively speaking, in computer standards. And now, given a word you would like, which is misspelled, you would like to find the closest word in the dictionary that match your word, right? And the question is how to do that. And one natural way of doing it is the edit distance. And before going into the formal definition, edit distance is roughly how many edit operations you need to do to get from one string to the other. So the way to think about it is that I give you the string in an editor, and you need to edit it to get the other string, and you're allowed to doing the following operation. You're allowed to move the cursor, but only from left to right, just to keep things simple. And when you're on a character, you can either delete it or insert a new character before it, or keep it as it is, just move the cursor to the right, which is for free. Or alternatively, the third option is to replace the character, right? So essentially, insert, delete, or replace for every character except for, skip, which is free. So for example, moving from food to money, you replace F by M, right? So you have to pay 1 for that. Then you move the cursor to be before the second O. You insert an N. So insert. So this is 2. And now you have to change the O to E, mond. And then you have to change the D to Y, right? So this requires 4 edit operations, right? Right. Was it 4 or was it 5? Let's see. 1, yes. 1, 2, 3, 4. Yeah, 4 edit operations. So the edit distance is 4. And you can convince yourself that you cannot really hope to do better, right? So let's see why. Well, you have to delete one of the O's. You might as well change it to E, right? Because that's the most effective use that you can do. But if you do that, then you have to insert an N. So that's 2, right? Then you have to insert Y, and that's that. Now, of course, and of course the F, I forgot the F. You have to change the F to M, right? So you have to do all those operations. So 4 is the minimum price. But if I give you 2 strings, it's really not clear what's the minimum optimal solution here is, right? Because it might be that there are several possible solutions and it's completely not clear how to do it efficiently. And, frankly, I'm not sure I buy my argument that this is the cheapest solution. So we want a more systematic way of computing this edit distance. One cute way of thinking about edit distance is as alignment, right? So you put the words and the 2 strings, one on top of the others, and then you match them in columns, right? Well, the idea is that if you put 2 letters of the strings, you put them, of course, left to right. You're not allowed to scramble the letters. If you put 2 letters that are equal, this corresponds to when you edit, you do nothing, right? And then if you put 2 characters that are different, this corresponds to change, right? You're changing a letter. So we have two change columns here, right? One and one, you have to pay for them. Then you have a column where you match no character to a character, which means that when I move from food to money, I have to insert the E. So this is another one. And this is change, right? Now, the beauty of this interpretation as alignment is that it also works in reverse. If you want to move from money to food, then you just interpret things in the other direction, right? So it says, this is change column, this is keep the same, this is change column. This is now a delete column. It says go and delete the E, right? And this is a change column, right? So now the question becomes, I give you two strings, how to align them in a perfect, in a way where you have to pay for as few as columns as possible, where you have to pay for a column if it's an insert or a delete column or a change column. If it's a column where the two letters are the same, you don't have to pay. Okay. And there is, one can define alignment formally, but I hope you visually understand what it means, right? It's just, as I said, you write the two words in columns and you just put them together. Okay. So the edit distance problem is given to string, how to compute the minimum edit distance between them, the minimum number of edit operations needed to move from one string to another. And as I said, one nice application is in for spell checking. It in fact works surprisingly well. I don't think this is most of the way people, the way most spell checkers work nowadays, because you can do other tricks. You can do tricks that are related to what are the kind of mistake people frequently do and so on. So you can be a bit more intelligent about it than just edit distance. But I have a spell checker, that I wrote using edit distance, and it works surprisingly well. Sometimes it works much better than the standard spell checking. Things like diff, right? You want to compare two files. Then if you think about what diff does, it essentially does an alignment of one file against the other. Essentially, it does edit distance. And the big application that is extremely important is for DNA alignment, right? So the basic problem is that DNA is a very long strings, right? It's in the billions, I think it's in the millions of characters or even longer. But the problem is that, by the way, I think the longest DNA sequence belongs to some plant. So humans don't have especially long DNA compared to other things in nature. So you have this long string, which is the DNA string, which is essentially, you can think about it as a string. It's linear in structure. The problem is that we don't know how to read it completely, right? So we can, with current technology, we can read chunks of it. And those chunks that we read can be overlapping and so on, and we don't know the order of those chunks. So there's a huge amount of work on how to take this soup of chunks and how to align them together and so on. So there was the Human Genome Project a decade ago, I guess, or maybe a bit more by now, which was the project of how to get, to read the human genome and generate a complete reading of the genome of people. And this project, it was a huge project. And nowadays, it's, you can get partial reading by, sending your DNA to various sites, and they give you back things like your ancestry and so on. It's also a way for you to share with the federal government your DNA in case you feel like you need to share it. There were some recent cases in California where they found a serial murderer 20 years ago, 30 years ago, because, some niece of his or somebody, did this DNA check on one of those sites, and they realized that they have a family relative, and they could find this guy. So We are going towards an interesting universe where, our DNA is going to be available and can be used for various things. Some of them good, some of them not so good. If you're interested in the topic, there is a very nice science fiction movie called Gattaca. And this is completely tangential to the lecture, so let's go back to the lecture. To use DNA, you need a slightly more robust measure. And I would say, by the way, that in the real application, the DNA is even, the application is, the measure is even more complicated because you have to take into account things like, a portion of the DNA might flip or, and stuff like that. But, this is the kind of the initial metric, which is very simple. So the idea is that you have to pay for a gap, what we call insert or delete. There is a price delta. And then there is a mismatch cost, which means that if you are mapping a letter P to letter Q, you have to pay a certain price. And the reason is because of biological reason, different letters, and I'm doing an air quote here for letters, have different frequency of being signed. And of course, any distance is the easiest case where the pricing is all uniform. Okay, so this is it. Next, we will speak more about the alignment interpretation because it turns out to be the right way to think about this problem.